Thank you. A couple of thank yous actually to start off the webinar. First of all, to EU Green Week for allowing us to take part in the week and do this webinar. And secondly, to the EU Commission, to the Horizon 2020 programme for saying yes to the smart energy services to improve energy efficiency in the European Building Stock project, otherwise known as SENSEI. My name is Samuel Thomas, and I'm a senior advisor to the Regulatory Assistance Project. We're a non-partisan NGO dedicated to accelerating the energy transition, and we are a SENSEI project partner. Joining me today are colleagues from two other SENSEI project partners, Sotiris Papadelis, the director of HEBS, a Greek ICT company developing tools to facilitate energy transaction models. And Sotiris will introduce the eensight tool, which is the main presentation on this webinar. And Sven Voits from Factor 4, a Belgian company which focuses on performance-based energy efficiency projects, comfort improvements and maintenance of buildings. And Sven's going to respond to Sotiris's presentation and set the stage for the all-important discussion that will follow in the second half of the webinar. First, I'm going to just spend a few moments introducing SENSEI and setting the context for the coming discussion. The SENSEI project, it's funded by Horizon 2020, the EU framework programme for research and innovation. And the project aims to elaborate pay-for-performance schemes for financing energy efficiency in the building sector that could be implemented across the EU. It's looking to integrate those schemes within the preparation and implementation stages of energy performance contracting models and to turn the concept into successful business models and service offerings. Now, what do we mean by pay-for-performance schemes? We mean payments to energy efficiency service providers for estimates of the energy savings delivered using energy meter data. And that contrasts strongly with the current norm for building renovation programs, which are based on payment on the delivery of intermediate outputs like insulation, heating systems, air conditioners, etc., and not the final outputs that determine the success of the low carbon energy transition. Now, just moving on to our next slide. I see metered savings becoming much more important in the building sector for at least three reasons, and I'm sure there are many more, but I'm going to focus just briefly on carbon targets, firstly, secondly on ensuring grid reliability, and thirdly on cost effectiveness for consumers, for bill payers, for taxpayers. So starting with carbon, the importance of getting building renovation right is really underlined by last year's renovation wave announcement by the European Commission and the succeeding EU Commission Carbon Plan Impact Assessment. And in those documents, they foresee a reduction of 60%, 60% in direct carbon emissions from buildings by 2030. So that is a massive decrease in emissions that the Commission is hoping to see. Now, to help reduce emissions in the sector, the Commission is currently working up proposals, and they're going to be announced in July this year. They're likely to include carbon pricing, perhaps a new emissions trading system covering the building sector, regulatory drivers for building owners, for example, through minimum energy performance standards, forthcoming in the Energy Performance of Buildings Directive, and perhaps higher energy savings obligations for member states through the Energy Efficiency Directive. And the Energy Efficiency Directive, Article 7, is particularly important in this context. That requires member states to make energy savings attributable to policy measures. And 4 different measurement methods are allowed, but the overwhelming majority of savings are currently calculated using the deemed savings method. And that means ex-ante assessments of the likely savings from installing energy efficiency measures. And those don't really align the incentives of installers with policymakers. Installers are incentivized to deliver installations at least cost, and the actual outcomes in terms of energy savings is of less concern. But as the EU relies more and more on building renovations to deliver on its objectives during the 2020s, the pressure to use metered savings methods will grow, as policymakers are going to need much more reassurance that the subsidies going to the sector are actually delivering. So I would say watch this space when it comes to EU regulation. I think we're likely to see a greater emphasis on metered savings going forward. Coming back to the importance of buildings, the renovation wave is looking to double the renovation rate in the 2020s and go even further beyond 2030, as well as switching to renewable heating systems, for example, through heat pumps powered by electricity. And while the last vestiges of coal are driven out of homes, the other key leg of the Commission's carbon plan is the continued decarbonisation of the power sector. So if you couple an increasingly decarbonised grid, powered by a higher share of intermittent renewables, with the electrification of end uses, not just heating, but transport, of course, and the value of energy efficiency begins to change. It's not just about carbon savings, energy security, health, jobs. Of course, the list of the benefits of energy efficiency is long, but it also becomes about the value of energy efficiency to grid reliability. And that is only going to increase, but not in a linear way. The value depends upon the load shape of the avoided energy consumption. What time of year, what time of week, what time of day, as the famous duck curve from California so clearly exposes. In California, with solar generation peaking in the middle of the day and end-use demand ramping steeply in the evening as solar generation tails off, the value of energy efficiency that curtails load during the ramp and during the load peak clearly becomes more valuable in pure economic terms, but also in carbon terms, as is during the evening that it's the fossil generation peaking plant that begins to operate. So the value of energy efficiency will increasingly vary as the energy transition progresses. And that value will affect the economics of district network operators. At the same time, the EU has enshrined the energy efficiency first principle into its electricity regulation, which requires the consideration of the potential value of investing in efficiency, including energy saving and demand response, in all decisions about energy system development. So we've got carbon, we've got grid system reliability, but we also should be doing or looking to do more metered savings for the sake of cost effectiveness. It's not just about prioritizing energy efficiency for energy efficiency's sake, but to meet societal objectives more cost effectively. And this has been the fundamental reason for the development of pay for performance programs in the building sector in the US, where most of them are funded through obligations on utilities, where the costs of those obligations are passed through to bill payers. And with the application of the energy efficiency first principle in the EU, I think this will become increasingly more the case here too. But of course, cost effectiveness is not just about maximizing the benefit cost ratio based on central estimates of energy savings. Uncertainty also affects the willingness of parties to invest in energy efficiency. And this is where metered savings really make a difference. By putting in place what we can see here as a schematic representation of a metered savings approach. Energy savings, of course, cannot be directly measured. You can't measure the absence of something, but we can get a better handle on those estimates using ex post metered data. And all the programs in the US and in the ESCO market use a variation of this type of schematic. This one's adapted from Recurve, a company operating in the US, but I could have chosen one from IPMVP or any number of different operators in this space. They use post-installation energy consumption data to estimate the energy savings from efficiency interventions. But of course, that means comparing the observed consumption with a counterfactual, and that needs to be modeled, usually using pre-installation metadata, the baseline, and data from explanatory variables such as the weather that can be measured over both periods. So we can reduce that uncertainty in terms of what energy efficiency projects are delivering, but we can never completely get rid of that. And that's where the eensight tool comes in. And this is going to be the subject of our next presentation from Sotiris, who's going to explain his approach to trying to understand uncertainty better in terms of the impacts of energy efficiency installations in the building stock. And the main aims of what we're going to see next are, one, to basically introduce the tool, let Sotiris explain it to you. Secondly, to gather your feedback. And thirdly, and this really is the most important thing, to create a community to develop this work further. This is just the start. We want your own insights, your feedback on this tool, and we want your help to develop it in the future. It's all going to be open access so that we can hopefully develop the pay for performance market within the EU. So with that, I am going to stop and I am going to pass the mic to my colleague, Sotiris. Thank you very much.
Thank you very much, Sam. Let me share my screen. Okay, then. So, brief outline of what the presentation of the eensight tool is about. First, why the SENSEI project developed a new tool for measurement and verification. The project didn't start with the goal to develop something. The main idea was to review what already exists and see which tools and ideas that already exist fit best to the SENSEI goals and what SENSEI envisions as a business model. Then we discuss a bit about the tool as two different things, as a template for new models. So it's not just a model, it's a concept that you can derive different models from that. And we have already implemented a few models and hopefully we'll implement more. And also it is a tool to help experimentation, because the idea is that there is never a model that rules all. Okay, you cannot say a priori that this is the best model or this is the best approach. You have given the data and information about the building, you have to select the most appropriate modeling approach, and this implies that you have at your disposal a set of different ideas, different models that you can compare and see which makes more sense. And at the next step, hopefully, why makes sense. So, why we developed a new tool? We started with a review, and the review focused on what already exists in terms of open source tools. I'm pretty sure there are a lot of very interesting frameworks, but they are developed by companies that they use it for their own purposes. So we only had to review what already exists in terms of open source implementations, and in this case, there are not that many. So the domain, let's say, of things that you can test and take different ideas and combine and etc., it's quite limited. The second thing is that if you go to the literature, you can see a lot of ideas. Okay, the literature is quite extensive. You can find ideas from advanced models that use gradient boosting decision trees or probabilistic Bayesian approaches to quantify uncertainty, a lot of different ideas and methods. But there is a gap between having a methodology and then having a tool that implements this methodology so you can experiment with it and maybe take what you find most valuable for your purposes. And just because an idea looks good on paper doesn't mean that it makes sense for you to devote time to actually implement it in a tool and see if it makes sense for your purposes. And as I said, because you can never say that this is the best model, it's always good to have a more diverse set of models and workflows. So it's not a bad idea to introduce competing math and competing models into the domain. Okay, this graph is another graph that shows exactly the same thing that what Sam showed before. It's just to describe a bit. I'm pretty sure everyone in this webinar understands the concept, but very briefly, when you say metering energy efficiency, you are talking about having a tool that allows you to predict the counterfactual, to predict what the consumption would have been if an intervention had not taken place. So you have consumption before, you have consumption after, you have a way to make this prediction of the energy consumption if the intervention had not taken place, and the difference between the counterfactual and what you see, you can attribute it to the energy efficiency intervention. This means two things. One, that mainly when we're talking about measurement and verification, we're talking about prediction. It's a predictive problem. It's a problem of developing predictive models. And second, okay, it has embedded uncertainty and fragility because as you go further away in time from the time that the measure was installed, you cannot safely argue that the only reason why you see a difference between what you would have consumed and what you now see is only attributed to the energy efficiency intervention. Maybe we'll have time at the end of this talk to discuss about different ways where you can address this fragility. From this plot, let's just keep the idea that it's about, first and foremost, predicting. So we can start, although this is not the way we develop it, I think it makes sense in order to understand it, to start from a model that already exists. There is a very fundamental, very well-known model that's called time of week and temperature. And what it does, it models energy consumption in terms of the time of the week. And the idea is that days are different between them, but weekly cycles are more stable. So let's model energy consumption, hourly energy consumption, as a function of the hour of the week. It's something that takes values from 1 to 168, and also the outdoor temperature. Okay, in principle, you can add more variables, both categorical and continuous, to improve your prediction. We have an implementation for this model in eensight, where you can add more variables, but usually when you see this model, when you're talking about measurement and verification, especially when you link it with pay-for-performance schemes, usually energy consumption and outdoor temperature is the only data you have. So this model says for a different hour of the week, I have different consumption, so I use a binary variable per hour of the week, and then I model the relationship between consumption and temperature, and I make a distinction. I have two different, let's say, formulations. One for the hours where I think, and there is a heuristic for that, that the building is unoccupied, and usually this formulation implies a linear relationship, and another that's more flexible, so to capture U-shaped effects when it seems that the building is occupied. The interesting thing about this tool is that it does not explicitly model yearly variation. There's no variable that says month of the year or something like that. Instead, it follows a specific template. This template is the template that we use in eensight for all the models that, let's say, are derived as variations or extensions of this model. So if we abstract a bit the model, we can describe it into these 5 steps. One says, let's find a small set of observations that very well summarize the data set. You can call them prototypes because there is literature, especially in the machine learning interpretability domain, that calls these observations that summarize well the dataset prototypes. We'll call them anchors. But the idea is to define a small set of observations. Then let's define a distance, something that says how much any observation, any observation in my dataset is close or further away from its anchor. Then we take these distances and we convert them in weights. And this actually means make them to have values between 0 and 1 and make this transition between 0 and 1 quite smooth. Then instead of having one model that fits the whole year, fit a number of models, one per anchor, and use these weights to have a weighted regression. Weighted regression means that the model sees all the data, but it doesn't focus equally on all this data. The weights tell it actually that for some data it's important to fit it well, for other parts of the data not so much. So it's weights on the loss function. Okay? And then use this ensemble, these different models we have, to come up with a weighted sum of their predictions in order to predict energy consumption. So we don't have one model for the whole year. We have a number of models, each focused around a specific anchor. And if you want to think this in a bit more abstract way, you would say that the first 2 steps are actually what makes this template able to provide, to be a starting point for new models. You can always think of new models by playing with these 2 different ideas, finding different ways to define this small set of observations and find different ways to define distance between them. The other 3 steps are actually the same for every approach, no matter how you decide to define your anchors and distance. For the specific case of the time of week and temperature case, this small set of observations comes from days that cover uniformly the span of the calendar time. So you try to uniformly break the period that your dataset span into equal length intervals, so to cover uniformly as much as possible the span. And the distance metric is just the number of days between 2 observations. And the absolute number, so that doesn't matter if you compare A to B or B to A. And this is important because a proper metric must have this property. And if you want to visualize it, it looks like that. The upper panel of the plot is a data set that we used in the deliverable. eensight is actually the product of one specific deliverable of SENSEI, okay, the 7.1. And if you wanted to have, let's say, 4 anchors, then you would take these 4 different dates to evenly cover the span, and then you could put the weights in a way that says focus more on anything that's around the anchors and less anything that goes away. Very roughly, if you say let's have 12 anchors, so it's 1 anchor per month, and you can play with how these weights, how fast they go to 0. There is a parameter called sigma. You can play how fast or how slow they go go to 0. If you have sigma at a value of 0.2, you actually have Caltrack. The Caltrack model is a model that focuses individually on each month, and then it has this weight curve so that it considers a 3-month span. So, okay, that's a very interesting approach, but we have an issue, let's say, and this is how we come up to thinking about different approaches. Maybe the idea of the distance metric that the time of weekend temperature uses, the distance as the difference in days, cannot capture all the things that we like to capture in a specific data. What you see is part of the deliverable. It's part of an attempt to find and to provide a very easy and fast, etc. way to find similarities in terms of profile loads. So this approach is not meant to be used in an automated way. It's meant to be used in an exploratory way. You can play with it. The idea is you have a profile, a daily profile. Let's split it into a number of intervals, not overlapping intervals. In this case, it's 3. This is why you see ACA. So it's 3 8-hour intervals. Then you say each interval, let's discretize it using a number of levels. If you have 3 levels, you have 3 letters, A, B, C. So ACA would be all the profiles that have A level in the first interval, C in the second, A in the last. And if you do that, you can find similar, very fast similar profiles. And if you take similar profiles and then map them to the calendar space, let's say, you see that, okay, there is a rule here. The rule says that all these profiles, Sundays and Sundays not during the summer, okay, but you will never be able to identify or to isolate them if your measure was distance in days. So maybe we can think of different ways to define this distance between observations that allows us to somehow, let's say, rearrange this calendar space so that things that look similar in terms of their profile can actually become similar through the distance metric we use. Now, is it important to focus on profile similarity? One could say, okay, it's interesting, but not necessarily important if you want to have a good predictive model. The answer is yes, we wouldn't care so much for profile similarity if we had a lot of different sources of data. So if I have a lot of opportunities to explain what I see in terms of energy consumption, occupancy schedule, submetering data, etc., okay, profile similarity may not be that important. Also, if we employed some complex models that are able to find relationships, nonlinear relationships of themselves without our help, let's say, then maybe again, profile similarity won't matter so much. But if we are dealing with linear models, because we want it more interpretable, and if we are dealing with data such as energy consumption and outdoor air temperature, which is very limited data. In reality, you don't have a lot of opportunities to explain things. So it's a good idea to help, let's say, the model by asking to focus on things that are similar, things that have strong covariance, that are codependent, so that then you can ask, okay, let's explain the variability that I see in this subset of the data, but with the few things that I have that are able to explain variability, such as outdoor air temperature. Now, this is a testable argument. And by that I mean you can always play around with different distance metrics, and the eensight is actually developed for that, for testing and playing with different ideas. And you can see if actually it makes sense or not. Okay. Now, how we can adapt the time of week and temperature model so that we can make use, we can exploit profile similarity. We can change the distance metric. We can say that given calendar information, and there is a reason why calendar information is bold, given calendar information about observations, let's have a metric that tells us that these are close if their daily profiles are similar. Why calendar information is bold? Because just because you have similarity in load doesn't mean that you should say, okay, let's treat this subset as something concrete. You never know, again, because you have limited data, if what you see is actually something that persists, something that generalizes. So it's always good, let's say, if when you have a cluster of similar profiles, you also have a rule, something that somewhat explains why these are similar. Your best bet is to explain it through calendar information. If I see that they are similar, but also they are Sundays that are not summertime, that's a rule that you can feel confident that probably generalizes. Probably it will repeat itself in data that you haven't seen. And one thing that you could do is to have clusters based on load profiles, and then just treat it as a classification problem and say, if I have a model that is given calendar information in these clusters, can it predict the clusters? If it can, maybe that means that there is a rule there. You don't have to know it, you just have to know that the rule exists. So using calendar information is important. And also because during prediction time, you don't have information about consumption. The only thing you have is this limited data about the time stub. So your best bet is to actually be able to use this information. And even though we have the calendar as something that says day of the week and week of the year, it's even better to have day of the week and month, because then you constrain even more your model. So if it finds some rule there, probably it's a rule that's repeatable. Okay, let's go back to the template. We said we can create different models by playing with these different steps, finding a small set of observations that summarize the dataset and define the distance between each of these prototypes or anchors. So how do we find anchors in the insight? Okay, the idea is to say that these anchors could be profiles that are repeated. Anything that looks like a pattern, looks like something that happens again and again, is a good candidate for having it as an anchor. And also, let's not use anchors that are similar to each other. Let's use as anchors profiles that are repeated but are very dissimilar to each other. And we have a methodology for that. I won't explain it here. It's explained in the deliverable. It's implemented in Insight. The only thing that I want to say about the methodology is that it's based on a concept that's called matrix profile. And if there is one thing to take away from matrix profile, is that it is a transformation of your data that tells you something about the predictability about your data. You can have two different consumption datasets that have the same variation, for instance. Or if you want to be able to compare the coefficient of variation, standard deviation divided by the average value. Okay, which one is more predictable, let's say? You cannot say by looking at the variation of your data. But you can say by looking at the variation of the matrix profile transform. What you see here is a matrix profile for a very predictable, very well-behaved building, because low values mean that daily profiles that you see there are actually repeated, or more accurately, that what looks like them looks very much like them. This is a way to say that something repeated. And you only see a few spikes that are daily profiles that are strange, that are not repeated in the dataset. They are not repeated in the dataset, maybe because something strange happened, or maybe because we don't have enough data. It could be, for instance, a holiday. And if you have just 1 year's period, you just see once this holiday. And if this holiday, the consumption during that period is different from, let's say, Sundays, for instance, but it's different. You don't have anything to compare it with and to say, okay, I see it more than once, so it looks strange. But low variation in matrix profile is a good indication that the building is well behaved, that it's predictable. And okay, the methodology that finds the anchors, it's what it does conceptually is to take one day from the low values and then finds as the next anchor another one of these low values that looks very dissimilar to the one that you have already selected. So it's the iterative process that at the end it gives you these anchors. If you follow this process, and we explain in the deliverable also the stopping criterion, because if you allow it to run, it will exhaust your data set. But it's very easy to understand when you have started picking redundant profiles. If you allow this to follow, to evolve, you can pick up your prototype profiles. The reason why I have this plot here is to show that it's a very different way to think in terms of anchors or prototypes. It doesn't matter where they are located in your time span. The only thing that matters is that they are repeated and they are different to each other. And this is actually a good definition of what a prototype, what an anchor should be. And now that we have the anchors, we want the distance. We want to have something that we give it as information, temporal data, temporal calendar features, month of the year and day of the week, and tells us how much similar the daily profiles are. And for that, we do something called distance metric learning. Okay, granted, we use the simplest approach inside, but we experimented with more complicated ideas. So conceptually, the whole idea is that you give the algorithm things that are similar and things that are not. And you say to the algorithm, okay, find a way to distinguish them. So the algorithm takes these anchors and then finds profiles that are similar to its anchor and tells the algorithm these two are similar, and they are similar because they are similar both to the anchor. And it's also easy to find dissimilarity. And if you actually take the new distance metric and you do the same thing that we did for the time of week and temperature, you get something like that. How the weights change per anchor throughout your data set. It doesn't look intuitive, okay, but it wasn't meant to look intuitive. The idea was never to have smooth weights. The idea was to be able to fit different models in different parts of the data set in a way that makes sense. And the question is, does it make sense? The answer is yes. And it's again testable, and I will say about that in the few moments I have left. It's never worse than something like the time of week and temperature. For very well-behaved buildings, is a little bit better in terms of accuracy. It becomes significantly better for less predictive buildings. Keep in mind that we're talking about optimized models, so anything that's parameter first is optimized and then we compare. Second, it's not just one model. You can play with this idea. You can split your data into intervals and fit different models in different intervals. This works even better. You can say, okay, I have a problem with the anchors because I'm not sure, okay, they are repeated, but how many of the profiles are similar to that, maybe just a few. So you can discard the anchors and then find a new clustering, a new ones based on the metric that you found. And this works even better. But the important part is, okay, you can start from this process, start developing different models and etc. The idea is to be able to compare an experiment. And so it's not to say, okay, this is the method, this is the model. The idea is, let's devise different models and let's see what makes sense in which cases. And for that, the insight, a lot of effort in making it easy to run things and to test. So we have command line tools. The idea is to make it easy to run it on different data sets without any knowledge of programming. Okay, the actual library is implemented in Python, but you should have to know Python. You can run it on the command line by giving things like a catalog. I'll say a few things, the parameters, and also you can enable tracking, which means that it logs all parameters, artifacts, by that I mean intermediate data sets or models and metrics, so you can compare. In order to, the idea of making an experiment is to then be able to compare and see what makes sense or not. This is a data catalog, so you don't have to write code for data loading and saving. You just tell the model where to find the data. Data D has these question marks because it means if you don't specify it, you have to inject it later. Data sets are different stages, raw, intermediate, and that ends at the model results, let's say. There are specific classes that know how to load and save data, so you don't have to care about that. The only thing that you have to care is to give it a file name, to give it some parameters for these loaders. If it is a comma separated file, is it actually a comma or something else, for instance? If you want to create two versions of the model, of the data, one for train and for test, this is also similar for parameters. To avoid having users to write code, they can actually edit files and give different values in these files, and these command line tools read these files and run them, so you don't have to directly work with a library. The moment you say, okay, enable tracking, you actually enable something that's, okay, it's not developed by us, it's something called MLflow, but it's a framework that allows you to log things and to compare things in terms of inputs, outputs, okay, in terms of parameters and performance metrics. And it's actually maintained in that address. We're still expanding it. We have a few ideas of how this can become even smarter, even better. Okay, I finished and I think I'm on time. Yes. Everything is on GitHub. Everything that works. There are things that are being, or maybe we'll answer to questions later or to all of them. But because I just saw something that says if it is on GitHub, yes, it is. The parts that are tested, but we're still adding things. For instance, we had a gradient boosting model. It's not there yet. We will reintroduce it. Gradient boosting model is a very interesting model for benchmarking. And also it's interesting because a lot of things that work well for a linear model, for instance, I don't know if you have time, but you can say that instead of trying using your model to predict energy consumption, let's use an anchor as a prediction and use your model to correct it, to find out how to explain the difference between that prediction and this approach works very well. This prediction works very well. for linear models. It doesn't work well at all for gradient boosting models, for instance. So we will introduce again the gradient boosting model when we know the conditions under which it makes sense to be used. For instance, the only thing that I can tell you definitely works well with gradient boosting models is this here. What is a... Yes, is if you say that anything that is spike and strange, I don't allow my model to see it at all during training. This works very well for gradient boosting models. But anyway, okay. I think I'm finished.
Okay, thank you, Sotiris. Yes, there are already some interesting comments and questions in the remarks. I would just like to present to you a few ideas, or to say, yeah, a few suggestions maybe where for some applications of this tool. First, I want to try to summarize what the tool does or can do. So Therese, correct me if I'm wrong, but what I understand is that your tool does not take the whole data set at the same time and makes one model, but you split up the data set in different categories of daily profiles that look similar. And then you make a model basically for each of those categories. And then if we go into the reporting period where we have to estimate the energy savings, first you check what kind of a profile or what kind of day is it that we are talking about, and then you take the model for that kind of day or that category, and then you predict the profile for that day. That's what I remember. I'm not a software engineer myself, but
yes, and you can also, anything we show it's daily profiles, but you can split it. You can have intervals, and the idea of splitting them comes back to what Sam showed, that maybe you have different value of energy efficiency. So maybe you care about a model that it's works better in some periods than others. So let's split the data and focus on the period you care about, for instance.
Okay, and so you said that basically this method is always better, especially in the case where we have a building that is difficult to predict with or difficult to model with one model.
Yes, I had ever seen a case for the data sets. We are working on a paper that does what I see in one question here about a complete study comparing the tools. From what we have seen so far, playing around with different data sets, because the whole idea is it's really based on trial and error. Okay, you use different data sets, and for what doesn't work in a specific data set, you try to say, okay, what can I do to improve it? We have seen that, generally speaking, it's never worse.
Okay, so it's always better or the same.
Yes, marginally better if you can, if there is a lot of predictability and a lot of, to say, a lot of things are repeated.
Yeah, I see.
On a similar schedule, let's say. And it's better if things are more erratic. Of course, it has limits, okay? If a building is crazy, but I haven't seen any data set for that. I'm sure there is, but I haven't seen a data set where the building acts crazy, so no model would work. I'm pretty sure there are.
Okay, good. I wanted to present a few projects or maybe possible applications that, I think that this tool may be in handy or may come in handy. First, I have to say there is absolutely no action taken already to use the tool in those projects, so it doesn't really, it's not really already a practical use. But I just wanted to have your and everybody else's view on whether it would be possible to use this tool in this kind of projects. So first, I wanted to say who I am. I'm Sven Nuits from Factor 4. We are a small consulting company in Antwerp, in Belgium. We are an EPC facilitator, and sometimes we also act as an ESCO in the private sector for SME projects in SMEs. Personally, I'm an MNV professional and an energy consultant. So Factor 4 is one of the partners also in the SENSEI project. I have two practical applications, or two ideas for a practical application of the tool. One is an application in a government program called Plage, which is a program in Brussels, and another project is a project for an ESCO in which is basically an office building with some storage space also. I will briefly present the two projects and then illustrate how or what I think that this tool can do in this kind of projects. First, the government program Plage is, as I said, in Brussels. It is a program where all the large buildings have or are imposed a mandatory energy saving target. So they have to reduce their energy consumption per year, and it depends a little bit on as you can see here, it depends on the current energy use per square meter. The more you are in the red, the higher your target is. So it goes from 0 to 20% energy saving per square meter. And so it is a system where the government sets a cycle of one programming. So they have one year time for the programming. So they have to prepare the project. Then they have 3 years of execution time, so they can implement a few energy measures that can realize this energy reduction. And then at the end, there is a 4-month evaluation period. So this is a typical energy saving program that could benefit from this kind of tool. Of course, you in this program, the building owners have to really prove what, or they have to prove that the energy measures that they are taking do have an effect. So they have to prove the energy saving. So the choice between two possibilities for measurement and verification. The first one is a standardized MNV tool that is developed specifically for the Plage project, where we use standard variables. Basically, they are the degree days, and there is a short accuracy check. So they just have to enter their energy data, which is mainly monthly data for heating consumption, and they have to enter the data, and then the system processes the data and it can do an accuracy check in advance. If the accuracy check is not sufficient, then that means that the model that is the standard model does not give the good or the best results. Then they have to make a dedicated MNV plan, which will include specific independent variables or static factors and so on. And they have to do this in accordance to IPMVP. So the MNV plan has to be submitted for each building, a different MNV plan, and it has to be IPMVP adherent. So, but for this project, if we could devise a more accurate or a better automated tool for the first the standardized tool, that would be much better, because it takes a lot of time and effort for each of the building owners to develop their own MNV plan and to do MNV separately. Also for the government to check all the models and the and the plans. That's also very time inefficient. So in this case, I think the tool as proposed by Soteris would be a great improvement. Sorry. A second practical application is in an ESCO project. It's a project where Factor 4 was the ESCO. It's we call it an EPC project, a light EPC project. It's not a full option long-term energy saving project, but a short-term program, 2 years. There are three buildings on one site. The floor area is about 6,000 square meters. It's not a very big project, but and also the financing is not included. So the building owner did the financing themselves. So there were a few measures were implemented, and they paid for the measures themselves. So it was not paid by the ESCO. There was, however, a profit sharing incentive for factor 4 for the ESCO. So, but in the end, we managed to realize 31% energy saving on the gas and 9% on electricity. What we applied here was a very much simplified MNV because it's such a small project. It doesn't. It's not really realistic to install a very complicated and advanced MNV or metering system. So we didn't do that. So it was a very simple regression model in Excel based on the heating degree days, and they manually recorded the metering data at this moment. And for the electricity, we just used an average per month. So it's not a very complicated model, but the cost savings or the energy savings were large enough to allow for such a simplified MNV. So after the 2 years project and the profit sharing, there is still a follow-up after those 2 years, and this is at this moment still going on. We're just monitoring the energy savings to see if the energy measures or the measures that we took are still having the effect that they are expected to have. So during this follow-up phase, this eensight tool could be very interesting, but we would need much more detailed data needed, hourly data, for example. We don't have that at this moment, but it could also it could be very useful to monitor the ongoing building energy performance. At this moment, we do it just monthly, but it could be very useful if we have daily profiles involved, and for example, and if we could check on a daily basis if there are any anomalies, and that there could be alarms set to this. There are at this moment systems that already have this capability. We don't use them in this project, not yet, because it's such a small project and the cost would not allow for this to do. What would also be interesting for us, I think, or for ESCOs, is that in smart buildings that really allow for flexibility, for example, with the heat pumps or with the storage devices, it could be interesting to use maybe this kind of model as for model predictive control of the building. If we can in some way use the models that used or the tool, if we could use this somehow to predict the behavior of the building in the days to come, then we could see if the building control could be adjusted or optimized using the prediction. I don't know if it is possible. I'm just trying to throw it in the group, and maybe we will see. Maybe Sotiris can explain on this already. So 2 very short presentations of 2 different projects where I think the tool could be used. I'm not, the goal of this webinar is to also get your feedback, so feel free to put your remarks or comments in the chat window. We will try to register. Them. So what are your ideas or suggestions? I noted down a few aspects or a few things as inspiration. We would need very detailed data. I'm sure that here in Belgium, at least, there are not too many buildings that have really very detailed data on energy consumption. Usually, it's very limited. What is the need for a human in the loop? How can this tool be made automated, or how can we make sure that the tool works without a human having to check everything? So this is something we could think about. Can we use it for grid management? How does it work with aggregation? If we have a building stock of 100 buildings, can we aggregate them? Can we just, or do we make a model for each building separately and then put all the data together? Can we use it in program evaluation, as I explained before? What do we do with non-routine adjustments or change in static factors? I saw that there was a comment before, someone asking what is how does the model or how does the tool deal with situation where you have a different comfort level before and after the measures? How can we take care of that? That's basically a change in a static factor or a non-routine adjustment. Is a tool? Is it possible to implement this or to take this into account? How is the uncertainty or the accuracy calculated or measured? And can we make a difference between the avoided energy use or normalized savings? Those are two. It's basically a concept that is from the IPMVP. The difference between avoided energy use and normalized savings is that in normalized savings, we calculate the savings in a normal situation. So an average year, for example, this, I don't know if this is possible with the tool that Sotiris proposes. And maybe at the very end, or last but not least, I can mention the advanced MNV testing portal. This is some tool that is developed under the wings of EVO, and they have a testing portal where if you have an advanced MNV tool, you can upload or you can download a data set, and you can make a model based on this data set and then compare it to other models. This is maybe very interesting. I don't know if Sotiris has already thought about this or if this is something that we could envisage for this tool. I just want to invite everybody to comment on what Sotiris has said or any of us have said. We will try to organize this discussion with a whiteboard that Victoria will show. We try to record your comments and your questions, and write them in the chat, or you can also raise your hand, I think, in the tool, and then we give you the speaking stick. How is it called? I don't know if there's anybody who would like to comment on what was said. The floor is open. If all goes well, Victoria can share the whiteboard that we can use.
Yes, actually, we switched. So Sitzel is going to share it. Here it is,
okay,
and I will
awesome.
add the comments.
Okay. Good.
I just added the 3 points that were put in the comment section on the chat.
Okay, I don't know if there is anybody who would like to discuss or add something by just switching on the microphone. Otherwise, we just go through one of the comments that are here. Maybe we, Sotiris, maybe you can say something about this first comment that was made. That is, how about the difficulty to estimate energy savings in this poorly isolated building where you have the design temperature or is not even met before, and then after the measures that have been taken, the building is better isolated and the comfort level is higher inside the building. How do you take care of this, well, or how can you?
It's actually it's part of a bigger question. The bigger question is what are the limits of the whole idea where you use historical data to fit a model and then use it to predict the counterfactual, and then say any difference that I see between the prediction and actual is attributed to energy efficiency. One aspect is this: maybe your historical data do not contain operational aspect conditions that you meet after the intervention. Maybe what happened is actually the same problem, is that your data is, the historical data was very accurate, okay. After the intervention, anything you see is can be attributed to energy efficiency, and then something happens. And this renders this baseline predicted model more or less irrelevant. And this can be very specific for a building, or you can go to this issue now with COVID-19, where you have a lot of buildings that change their operation. People work at home, for instance. And this affects a lot of buildings at the same time. And now you cannot trust, let's say, your model. And the answer to this is that, okay, it's a limit of the approach whatsoever. Okay, you cannot really squeeze out of such a predictive model. It doesn't matter what model you use. Okay, you can use any type of model. It's very difficult to squeeze out of it things that are not there in the beginning. So maybe if we are talking about aspects like different operations before after, you need to couple the model with some smart testing period where you actually test different conditions and you create more data than just energy consumption and output temperature. There's a limit to what you can do with having only energy consumption and output temperature, no matter what model you use. Maybe you need innovation in terms of the contracts, for instance. We are talking about ESCO contracts that couple with the model, and not just innovation in terms of models. For instance, one thing that we are very interested in pursuing and doing with this model is focus not so much on energy savings, but on efficiency, on estimating efficiency gains, efficiency improvements. And the reason for that is that if you focus only on savings, then you have a business model that's very different from all other output-based business models. In all other output-based business models, you have an asset, and the more you use it, the more value there is. This would be the case also with energy efficiency. If you see increased consumption, this means increased usage of the asset that's called energy efficiency, so it is more value. If the building is empty, for instance, then maybe you should think in terms of contracts that approach energy efficiency as a capability that has an option to acquire it. This is the cost to actually do the intervention, and then value from using it, from exploiting it, and make sure which costs and values are allocated to the different participants in the contract. A model can do so much, okay? So, and this fragility of things that change after the intervention and make the model, render the model not so much relevant, is actually a very good motivator to think in terms of creating a baseline model, using it, let's say, for the first year or something, and then going forward, discarding it. You cannot use such a model for a long time because it deteriorates, and you have something like it's dying a little bit every time you do a non-routine event adjustment. It's dying a little bit, so don't try to keep it alive. So if I had to say one thing is you need more than innovations in modeling to track all the uncertainties and difficulties in energy efficiency metering.
Okay. That's clear, I think. And if anybody wants to comment, feel free to raise your hand. I suppose that there is a raise your hand button somewhere, and that we will see it. If not, maybe we can move on to second comment that was from Connor. His question is there a scope for the method to to also allow testing and experimentation with ensemble approaches to modeling. I'm not really sure what he means by ensemble approaching to modeling, but maybe Paolo can explain a little bit, or if
I assume there are two ways to do ensemble modeling. Okay, one is to take the same model and fit it on different parts of your dataset. That's one way to create an ensemble. So now you have a lot of versions of your model that, because they see different parts of your dataset, they tell you something about the uncertainty of your method on unseen data. Okay, this is one thing. Maybe when Connor says ensemble, things in terms of gradient boosting methods. Gradient boosting methods are methods that build very simple trees that each one learns on the error of the previous, and then you have an assembly of these small trees. Each one of them is not very good in terms of predicting. All of them are very powerful. Okay, what is the issue with this approach? Okay, first of all, what is the issue with the first approach? It works very well as a way to say something about uncertainty. It's computationally intensive a bit. If you think in terms of using cloud-based resources, it doesn't matter. You can fit a lot of models, etc. If you want to test on your desktop different ideas, it becomes computationally expensive fast. The second idea of the gradient boosting models are very powerful. The issue I have with them is that I find it very difficult to optimize them. And by optimizing, I don't mean the usual approach where you optimize the hyperparameters. This you can do. Okay, you can have an optimization process that tests different configurations for different parts of your data and see which configuration makes more sense. What I'm saying is that you have a model, fine, and then you say, okay, how can I improve it? It's very difficult to find a way. It's very difficult to do feature engineering because many things that make sense to you doesn't always make sense to the model. Because the model is very flexible, it learns its own things. For instance, linear models or models that are linear in terms of their terms work well even when you cross-validate them with shuffling. So when they see different parts of your dataset and you have holes and you ask this model to fit it, it makes sense. It's not that bad of theoretically it has some aspects. It's not that bad of an approach. You will never do this for a gradient boosting model, because the model learns things that it shouldn't. And okay, personally, I don't know why, but I have seen it. It learns things that it shouldn't. So it's a good model to have it, let's say, as a benchmark and say, okay, we have this model with this very few approaches to optimize it, and then compare different things to that. But the reason why we're not so fond of it, and we had it in eensight and then we remove it, but we will add it again as a benchmark, is that it's difficult to find good feature engineering approaches that improve it. And even if you improve it, it's very empirical. You cannot be sure why. So this is about the ensemble models.
Okay. There's food for more thought, I think, with that. Maybe we can switch to this comment. Let me first check if I can change the color of the ones that we already discussed. But maybe this one, can we what would be the minimum requirements for the baseline to extract the anchors from, for an ideal length of a data set? Or
well, that's an interesting question for a lot of reasons. First of all, there is no reason to believe that it's any different than Caltrack. I mentioned it because I see a comment about that. Caltrack says 1 year, and it makes sense. Okay, if you have less than 1 year, then you have periods that you don't know what's happening in the building. So you can predict, but you cannot be sure. Okay, if I give you data about spring and summer and winter and tell you something, let's predict summer, maybe you're right, maybe you're wrong. So you need a full year. Okay, so far. But then you say, okay, how do you evaluate the accuracy of the model? If you evaluate the accuracy of the model in sample, if you see how well it predicts data that it has already seen, this is useless. This is absolutely useless. It doesn't make any sense to say how well your data fits the model, how well your model fits the data it has seen. This only tells you something about how flexible your model is. You can make it a little more flexible, and just because you account for the number, let's say, of parameters, it doesn't help much. If you want to say something about accuracy, you have to test it in data that it hasn't seen, and usually you cross-validate. But the moment you cross-validate, you do exactly that. You keep some, if you have 1 year data, you keep some months and you ask it to predict. So by that I mean, ideally you want 1 year, but routinely, even when you have 1 year data, you evaluate your data with less, your model with less. And usually this is a good indicator of the accuracy. So what the model can understand about, except if, okay, you're building, does during summer something very different from what it does during the other months, let's say. What your model can predict for summer, let's say, given only data about winter, spring, etc., it seems to be, at least empirically, a very good indicator about what your model can do if it sees a whole year's data, and then you ask it to predict next year. So ideally, you want 1 year data, but you always, even if you have 1 year, you evaluate it with less. But there's no minimum requirement. I mean, it's more an issue that you have to at least have 1 year data, but it's one of the things that, okay, more data is always better. And if you don't have data about a specific period for specific months, you can expect that you will not do well with that. And this comes back then to how you quantify uncertainty. And we never mentioned in the presentation anything about uncertainty, because when we started working with eensight and the deliverable, we thought that uncertainty is actually quite simple. I mean, you cross-validate. When you cross-validate, you have errors out of sample. You have errors that described how off your model is to data that has never seen. So it makes sense to say, okay, you can use this as a proxy of uncertainty. But it's the more you see about it, the less straightforward it is. And now we have started experimenting with, and we'll see where this leads, to actually having approaches that create new data that look like the data you have, that you used your model to train it with, as a better proxy to uncertainty.
Okay.
Depending, okay.
I have one more comment that I find very interesting, is about a question about transparency. And the other tools like Caltrack, one of the advantages that it's relatively straightforward and comprehensible. The more advanced modeling we use, there is a danger of things becoming a black box. How do you think about that?
Okay, the answer is, you can have, first of all, we used to have inside the gradient boosting model. Now it isn't there, the models are linear. In order to be more, a bit more transparent. But the transparency is not that straightforward. I mean, if you have a model that has, it's mentioned Caltrack. Caltrack has per month 350 parameters. It's a linear model with 350 parameters. What's transparent about that? What can you understand about a linear model with 305 parameters? So if you mean transparency in terms of methodology, some methodology, maybe it's easier to understand than other. Okay, yes, then maybe doing things that are more complicated may put off some users, saying, okay, I'm not sure I understand completely what this model does, so why use it? But I think the whole idea is to actually test things and understand when something makes more sense than something else. And in that case, you should strive at least for a minimum, let's say, level of transparency. So, okay, you can exclude neural networks, for instance, because they could work very well, although they don't. Neural networks work very well for other types of data, not so much tabular. But there are ideas there. You can exclude some models that you know are very difficult to understand what's going on and why the model works very well, for instance. And then anything that it is, let's say, a little bit more transparent than this upper level that you put, say it's how to say, a level field. It's okay. You can evaluate and test.
Okay, thank you. Check. Maybe another interesting remark is on the reference profiles for if we want to estimate normalized savings. How could we do this in the tool here?
The question is how you go from prediction to savings. Normalized means that it's conditioned on things that I observed. So when you say I predict energy consumption conditioned on time of year and temperature, it's already normalized. So you have normalized your energy consumption in terms of prediction. So if you compare this with actual consumption, then you have normalized savings. No.
Hello, Sotiris?
Yes.
Hello. So the question was for me. Actually, I know what you mean, but this is more like how to establish what are the standardized baseline parameters. Because you know the difference in the report is that you can have just saving based on actual consumption, or you can establish like a reference consumption based on standardized conditions, standardized temperature, for example, established on the previous baseline, something like this.
Okay, I understand. I think both are possible, but it's not part of the model. The model itself, it's a predictive model. But okay, it's an interesting thing that we can add to have two different approaches to compare and find savings. That's something that's not there, and I think maybe it's not at all mentioned in the deliverable, but it's something we can add. Thank you very much for it.
I think if I understand correctly, in the standardized normalized savings, you would have to have two models, one for the old situation, and that we can use this model to calculate what would have been the energy consumption in the normalized conditions, and then a model that describes the new condition, and so that we can calculate what would have been the energy use of the new situation in the standard.
That's what I understand too. Is it, Francesco, this is what you mean? You take counterfactual and actual, and you both lift something different. You both transform them, let's say, to a reference condition.
In short, the difference, if you do avoided energy use, you just take the condition in the report period, and that's all what you have actually. And when you apply normalized savings, you instead try to establish what are the fixed conditions you want to compare against. You know, also when they were doing usually like the energy efficiency evaluation in the past, you have like this typical year, something like this, but of course more advanced, because if you use more advanced model, then you need more parameters, more features in order to see what is the consumption you expect.
Okay. As I said, we haven't addressed it at all, but it's a very interesting thing to do so.
Okay, maybe we can have one more short question here is the one if the model can handle both electricity and gas consumption data.
It doesn't matter.
If you have sufficient data, I would say yes.
Doesn't matter at all. I would say that actually any model that all it has is consumption and temperature works even better when your main component of consumption is heating or cooling, heating in that case, than electricity. Because when you focus on electricity, okay, there is a component that says maybe you use electricity for heating and cooling, but you can see it actually if you play with different data sets that the contribution of the outdoor temperature is not that important given daily and hourly features, for instance. So the answer is yes, and for heating and cooling even better.
Yeah. Okay. And then maybe the last one here. What do you think the status should be? Should be a standard that is adopted by official instances, or do you think it will be a commercial product available to or both?
First of all, standardization. The reason why there is all this discussion about open sourcing things is that there is no standard. So you cannot be sure that a model, you can trust a model, for instance, because it passes standard. So maybe if you read the code and you understand the methodology, you can be more confident. But a standard for evaluating and verifying models is a very different thing than say take a model and make it a standard. Okay, I don't think any type of model should be a standard. Doesn't make sense to me. I would prefer a standard that actually allows any user to verify if he can trust or not a model. But a model itself being a standard, it's pointless. I mean, give me another domain where you have a model, it's a standard. About the commercial product, it's open source. Okay, if you have an open source code and you want it to do something commercial, the next step is actually to make it a service. But that's irrelevant. Service is engineering problem. It's not a methodological problem. So as it is right now, it's an open source tool for everyone to use.
Okay. Okay, and then maybe the last one. We are slightly over time, but there's only one more comment, so we can discuss it. I think is this one is a comment from Connor. I think Connor. I don't know if you are somewhere online or if you can explain a little bit, but the actual comment, can't find it in the chat box.
Track project. I don't know what a track project is. Curious.
Okay, maybe we can.
About energy efficiency performance tracking platform. And
Yes, I can't. Oh, okay, I decided it here. Does the eensight tool contain any open source code for determining data sufficiency for various modeling approaches? This could be useful for services that propose MNV modeling approaches such as the Horizon 2020 NTRAC project.
I will have a look.
Yeah.
the
Okay.
N-track project. I didn't know about
Maybe
this.
this is something we can come back to later with Conor directly.
Yes. Okay.
Okay. Maybe we should summarize here and actually invite everybody. So we will send an email to everybody that attended the webinar with an invitation to join the community and to discuss further with Sotiris on how to develop this tool further. I think that was the main goal of this webinar. I hope everybody got a first view or a first glimpse of what is possible and what is the current status. So we will come back to you via email. You will receive an invitation to join the community. Okay, then I think we can summarize or we can end the webinar here. Thank you everybody for listening and for interacting, and we hope to see you again in one of the further discussions on the tool. Thank you very much.
Thanks, everyone.